Space and time feel like two very different things. Space is the room around you, the distance between Earth and the Moon, the silent gap between stars. Time is the ticking clock, the aging face, the changing sky, the steady movement from morning into night. One seems to stretch outward, the other seems to flow forward. They feel so separate that it can be difficult to imagine why physics would ever place them together. And yet, one of the strangest lessons of modern science is that space and time are not truly independent. They are woven into a single structure called spacetime, a quiet, four-dimensional fabric in which every object, every beam of light, every planet, every breath, and every moment has its place. This does not mean time is just another direction you can stroll into, sadly, because that would make missing appointments much easier. It means that distance, duration, motion, gravity, and cause and effect are all connected more deeply than everyday experience suggests. Welcome to the Sleepy Scientist. Before drifting into tonight's subject, take a moment to get comfortable. Settle into whatever position feels easiest. Let the shoulders drop slightly, let the jaw unclench, and allow the room around you to become just a little quieter. This is a calm journey through one of the most beautiful ideas in physics, told slowly enough that nothing needs to be rushed, solved, or held too tightly all at once. And as always, if you're listening from somewhere out there in the world, whether it is late at night, early in the morning, or some mysterious in-between hour where the kettle feels like a philosophical companion, feel free to leave your location and local time in the comments. It is always lovely to imagine this little pocket of science being heard across different cities, countries, bedrooms, sofas, trains, and perhaps by someone who only meant to listen for 5 minutes and has now accidentally learned about space-time in pyjamas. If you enjoy calm, interesting science made for sleep, relaxation, or gentle curiosity, consider liking the video and subscribing to The Sleepy Scientist. It helps the channel reach more curious minds, tired minds, and minds that are absolutely convinced they are not sleepy yet, despite all available evidence. Tonight, the question is simple to ask, but not simple to answer. Why are space and time the same thing? For most of human history, it seemed obvious that they were separate. Space was the grand stage of the universe, and time was the invisible clock that measured what happened upon it. A planet moved through space, a clock measured time, a person crossed a room, a candle burned down. The two ideas worked together, but they did not seem to belong to the same physical thing. Then light began to cause trouble. Light did not behave quite like ordinary objects. Its speed appeared to be fixed in a way that refused to fit neatly into the old picture. No matter how carefully physicists tried to make space and time behave like separate universal backgrounds, the universe kept giving awkward little answers, like a cat calmly knocking a glass off the table while maintaining eye contact. The breakthrough came with Albert Einstein's special relativity in 1905, and then with Hermann Minkowski's space-time interpretation in 1908. Together, these ideas reveal that observers moving differently through the universe can disagree about distances, durations, and whether two distant events happen at the same time. But beneath those disagreements, there is a deeper structure that remains consistent. That structure is space-time. Later, Einstein's general relativity would go even further. Gravity was no longer described as a simple force pulling objects through space. Instead, mass and energy shaped space-time itself. Planets followed curved paths because space-time was curved. Clocks ticked at different rates depending on gravity. Black holes became regions where space-time was bent so severely that even light could not find a future path outward. So tonight, the aim is not to make space and time feel ordinary. They are allowed to remain strange. The aim is to make that strangeness understandable. Slowly, gently, and without needing to wrestle the universe into submission, the idea will unfold. Space and time are not two separate backdrops behind reality. They are joined aspects of one physical structure, and everything that exists moves through that structure. Even sitting still, you are moving through time, Even measuring time, you're doing it from somewhere in space. Every event has both a when and a where. Every beam of light traces a path through both. Every clock, every orbit, every falling object, every galaxy, and every quiet moment before sleep belongs to the same hidden geometry. And that is where the journey begins. Space feels like the place where things happen. It is the room around you, the distance from one wall to another, the long, dark gulf between Earth and the Moon, the deeper gulf between the Sun and the nearest stars. It seems like the quiet container of the universe, the invisible stage on which planets turn. Oceans rise, clouds drift, and socks mysteriously disappear between the washing machine and the drawer. Time feels different. Time is the order in which things happen. It is the clock on the wall, the changing light through a window, the slow cooling of tea, the difference between a seed and a tree, a spark and a flame, a child and an adult. Space seems to stretch outward. Time seems to flow forward. One feels like distance, the other feels like duration. In ordinary life, the separation feels so natural that it barely seems worth questioning. And for most everyday purposes, that picture works beautifully. A person can say that a cup is on the table at 7 o'clock, and nobody needs a theory of relativity to find the cup. A train leaves one city and arrives in another. A football moves across a pitch. A planet moves around the sun. A clock measures the passing minutes. Space tells where. Time tells when. It is clean, useful, and reassuringly sensible. Then modern physics quietly leans over and says, "Not quite." The title, "Why Space and Time Are the Same Thing," does not mean that space and time are identical in the ordinary sense. Time is not simply a fourth hallway one can wander down in search of last Tuesday. Space and time still appear differently in experience, and physics treats them differently in important ways. A ruler and a clock are not the same instrument, unless someone has had a very confusing morning in the laboratory. The deeper point is that space and time are not fully separate ingredients of reality. In the theory of relativity, they are joined into one physical structure called spacetime. This idea does not erase the difference between distance and duration, but it shows that the two are woven together. What one observer calls mostly space, another observer moving differently may partly measure as time. What seems simultaneous from one point of view may not be simultaneous from another. Motion, light, gravity, and cause and effect all reveal that space and time are more deeply connected than everyday intuition suggests. That is the central mystery. Human experience naturally divides the world into where and when. Physics, especially since the early 20th century, shows that the division is not as absolute as it feels. A moving clock does not agree perfectly with a clock left behind. A fast-moving object is not measured with exactly the same length by every observer. Gravity does not simply pull things through space. In Albert Einstein's general relativity, gravity changes the geometry of space-time itself. Even the order of distant events can depend on the motion of the observer, provided those events are not directly connected by cause and effect. This sounds strange because ordinary life hides the strangeness very well. People move slowly compared with light. Gravity on Earth is strong enough to keep feet on the ground and biscuits on plates most of the time, but weak enough that its deeper effects on time are far too small to notice without extremely precise instruments. The speed of light is about 300,000 kilometers per second, so fast that daily experience gives no direct feeling for what happens near that limit. Human senses evolved to handle trees, rivers, weather, animals, tools, and other humans. They did not evolve to casually notice that a clock on a satellite and a clock on the ground do not tick at exactly the same rate. So classical physics feels obvious because it describes the familiar world extremely well. Classical physics is the broad name for the older framework of motion, force, space, and time developed before relativity and quantum mechanics. It includes the mechanics of Isaac Newton, the study of fluids, much of classical astronomy, and the early physics of waves and heat. It is not a failed way of thinking. It is one of the most successful intellectual achievements in human history. It explains falling apples, swinging pendulums, cannonballs, tides, bridges, machines, and the paths of planets with extraordinary accuracy under the right conditions. Isaac Newton gave this picture its most powerful form in the late 17th century. In his great work Philosophia Naturalis Principia Mathematica, published in 1687, Newton described laws of motion and universal gravitation that could connect events on Earth with the motions of the heavens. A falling stone and the moon orbiting Earth could be understood through the same underlying principles. That was a magnificent unification. It suggested that nature was not divided into separate rules for the ground beneath human feet and the stars above human heads. The same mathematics could reach both. But Newton's universe rested on a very particular view of space and time. Space was absolute. It existed as a fixed, unchanging arena, whether or not anything occupied it. Time was also absolute. It flowed evenly everywhere, from the deepest mine to the farthest star, from the beginning of an experiment to its end, independent of who was watching or how they were moving. In this picture, all observers could disagree about position or speed, but there was still one universal time beneath everything, ticking steadily through the cosmos. For everyday life, this is so close to true that it might as well be true. The difference between Newton's time and Einstein's time does not matter when making toast, catching a bus, or wondering why one has walked into a room and immediately forgotten the reason. In weak gravity and at ordinary speeds, Newton's picture remains astonishingly reliable. Engineers still use Newtonian mechanics. Spacecraft navigation often begins with Newton's laws before relativistic corrections are added. The old theory is not thrown away. It becomes part of a larger theory, a very good approximation in the realm where human life mostly takes place. That is an important point because modern physics can sometimes sound as if it arrives by declaring the past silly and wearing a more fashionable lab coat. In reality, science usually advances by discovering the limits of earlier success. Newton was not wrong in the simple sense. His framework was incomplete. It described a wide and important part of reality, but not all of it. At very high speeds, in very strong gravitational fields, and in measurements involving light and precision timekeeping, the old separation between space and time begins to crack. The cracks appeared because nature refused to keep space and time politely apart. Light especially became the great troublemaker. It behaved in a way that forced physicists to rethink the meaning of motion itself. If the speed of light in empty space is the same for observers moving differently, then something else has to give. Distances and durations cannot remain universal in the old Newtonian way. They must shift so that the deeper structure of the laws of physics stays consistent. This is where the story begins to turn. Space and time stop being the silent background and become part of the machinery. They are no longer merely the stage beneath the universe, with matter and energy acting on top. In relativity, space-time is an active structure. It shapes motion. It defines the paths light can follow. It tells cause and effect where they may travel. In general relativity, it bends around mass and energy, guiding planets, stars, and galaxies not by invisible strings, but through geometry. The strange problem with space and time, then, is not that the everyday view is useless. It is that the everyday view is too small. It works inside the comfortable middle ground where humans live, but the universe is not limited to human comfort. It contains light moving at its cosmic speed limit, particles born in the upper atmosphere, clocks precise enough to measure tiny changes in gravity, stars dense enough to bend space-time severely, and black holes where the old meanings of distance and duration become profoundly altered. Space still tells where. Time still tells when. But modern physics reveals that where and when are not independent facts floating separately in the dark. Every event has both. Every object moves through both. Every beam of light traces a path through both. The universe does not seem to keep two separate ledgers, one for places and one for moments. It keeps one deeper geometry, one connected structure, one space-time. And once that idea begins to settle, the familiar world becomes quietly stranger. Sitting still in a chair is not truly stillness in the larger sense. A person at rest in a room is still moving through time. Earth is turning. Earth is orbiting the sun. The sun is moving through the Milky Way. The Milky Way itself is moving within the larger cosmic web. Every calm moment is part of a vast four-dimensional pattern, a woven record of locations, durations, motions, and connections. The old stage has not vanished. It has deepened. Space and time are still there in experience, as clear as the room and the clock. But beneath that familiar division, physics has found something more unified, more subtle, and more beautiful. The universe is not simply happening in space while time passes beside it. The universe is happening in space-time, and every event from the falling of an apple to the orbit of a planet belongs to that single hidden structure. Before space and time became space-time, they belonged to a much simpler and more familiar universe. It was the universe of Isaac Newton, and in many ways it still feels like the universe of common sense. Space was the place where things existed. Time was the steady flow in which things changed. A stone fell through space as seconds passed. A planet travelled around the sun while years went by. A clock measured the same time for everyone, everywhere, as if the cosmos itself had a great silent metronome ticking behind the stars. Newton gave this view its most powerful form in Philosophia Naturalis Principia Mathematica, published in 1687. It is difficult to overstate the importance of that work without sounding as if Newton personally installed the operating system of classical physics. In the Principia, he set out his laws of motion and his law of universal gravitation, linking the motion of objects on Earth with the motion of celestial bodies. A falling apple, a thrown stone, the moon circling Earth, and planets orbiting the sun could all be understood using the same basic principles. In Newton's picture, space was absolute. It existed independently of the objects inside it. Even if every planet, star, comet, and confused astronomer vanished, space itself would remain as a kind of invisible arena. It had three dimensions: length, width, and height. Objects could move through this arena, change position within it, and be measured against it. Space was not shaped by the objects it contained. It was simply there, steady and unmoved, like the most patient stage manager in the universe. Time was absolute as well. Newton imagined time as something that flowed equally everywhere, without depending on matter, motion, gravity, or the observer. A second on Earth and a second near Saturn belong to the same universal passage. A clock might be badly made, a pendulum might wobble, and someone might be late because they claimed traffic was unusually philosophical that morning. But beneath all those messy details, true time continued evenly. It was not personal. It did not stretch or slow. It did not care whether anything was happening at all. This made the universe wonderfully orderly. If space was a fixed stage and time was a universal clock, then motion could be described with great clarity. An object had a position. It had a velocity. Forces changed its motion. Gravity pulled bodies toward one another. With enough information, the future path of an object could be calculated. This was the grand promise of Newtonian mechanics. Nature could be described through laws that were clear, mathematical, and astonishingly effective. And effective it was. Newtonian physics explained why projectiles follow curved paths, why the moon does not fall straight down onto Earth, why tides rise and fall under the gravitational influence of the moon and the sun, and why planets move in stable orbits rather than wandering about like poorly supervised marbles. It gave scientists and engineers a framework for building bridges, firing cannons, predicting eclipses, designing machines, navigating oceans, and understanding everyday motion. For ordinary speeds and ordinary gravity, Newton's laws remained so accurate that abandoning them would be like throwing away a perfectly good map because it does not show every pebble. But even before Newton, there was an important clue that motion was not always as straightforward as it seemed. Galileo Galilei had described a principle of relativity for steady motion. He imagined being inside the cabin of a smoothly moving ship. If the ship moves steadily, without rocking or accelerating, experiments inside the cabin would behave just as they would if the ship were at rest. A dropped object would fall straight down, flying insects would move normally, water would drip into a container beneath it. Without looking outside, there would be no simple experiment to reveal whether the cabin was truly still or moving smoothly across the sea. This was a subtle but powerful idea. Motion was not always absolute in the way everyday language suggests. A person sitting calmly inside a train may feel at rest, while someone standing beside the track says the person is moving. Both descriptions can be useful, depending on the frame of reference. Newtonian physics could include this idea, but it still preserved a deeper absoluteness beneath it. Space itself remained fixed. Time itself remained universal. Observers might disagree about speed, but they were still assumed to share the same cosmic clock. That assumption worked beautifully because the world of human experience does not usually challenge it. Cars, trains, falling stones, ocean tides, and orbiting moons all move slowly compared with the light. Earth's gravity is strong enough to hold the atmosphere and guide the moon, but weak enough that its deeper effect on time is almost impossible to notice without precise instruments. So the Newtonian universe feels natural because it describes the realm where human senses live. The trouble began when scientists studied light, electricity, and magnetism more deeply. Electromagnetism did not fit quite as comfortably into the old picture. Light seemed to have a special speed, one that did not behave like the speed of an ordinary object thrown through space. If space was fixed and time was universal, then light ought to fit neatly into that background. Instead, it began to suggest that the background itself might need rethinking. Newton's separate space and time had carried physics to extraordinary heights. They explained a vast amount of reality and still remain essential for most practical work. But hidden inside the behaviour of light was a quiet warning. The universe was not finished. The stage and the clock, once thought to be separate and absolute, were about to become something far stranger. The first great disturbance came from light. For a long time, light had already been mysterious enough. It could behave like a ray, travelling in straight lines and casting sharp shadows. It could behave like a wave, spreading, bending, interfering, and producing patterns of brightness and darkness. It arrived from the sun, reflected from the moon, shimmered from flames, and slipped through windows with a confidence that made it seem almost ordinary. But light was not ordinary. Light was quietly carrying a problem deep enough to reshape the meaning of space and time. In the 19th century, James Clerk Maxwell brought electricity and magnetism together in one of the great unifications in physics. Before Maxwell, electricity and magnetism were often treated as related but distinct phenomena. Electric charges could attract or repel. Magnets could pull on iron and point compass needles toward north. Experiments by scientists such as Michael Faraday had already shown that changing magnetic fields could produce electric effects, and changing electric effects could be linked with magnetism. Maxwell took these experimental clues and shaped them into a single mathematical framework: electromagnetism. This was a major shift in how nature was understood. Electric fields and magnetic fields were no longer separate curiosities. They became two aspects of one connected physical system. A changing electric field could produce a magnetic field, and a changing magnetic field could produce an electric field. Together, they could sustain a travelling wave. This was not just a neat piece of scientific housekeeping, although physicists do enjoy a tidy cupboard as much as anyone. It revealed something astonishing. Maxwell's equations predicted that electromagnetic waves should travel at a particular speed. When that speed was calculated, it matched the known speed of light. The conclusion was profound. Light itself was an electromagnetic wave. What people saw with their eyes was part of the same family as electric and magnetic phenomena. Visible light, radio waves, infrared radiation, ultraviolet radiation, and other forms of electromagnetic radiation all belong to the same underlying structure, differing mainly in wavelength and frequency. But this discovery created a puzzle. Waves, in familiar experience, usually travel through something. Sound travels through air, water, or solid materials. Ocean waves travel through water. Waves on a rope travel along the rope. So if light was a wave, many physicists assumed it must also need a medium. This imagined medium was called the luminiferous ether. It was supposed to fill all space, allowing light waves to travel through the universe. The ether was an understandable idea. It was not a silly invention added because scientists had run out of sensible things to do on a rainy afternoon. In classical physics, waves normally had something waving. If light crossed the empty space between the sun and Earth, then perhaps space was not truly empty. Perhaps it was filled with a subtle, invisible substance through which light moved. The ether was expected to be everywhere, incredibly thin, and difficult to detect directly, but still physically real. There was a problem, though. If Earth moved through this ether as it orbited the sun, then light should appear to travel at slightly different speeds depending on its direction through the ether. A light beam moving with Earth's motion through the ether should behave a little differently from a light beam moving across that motion. The effect would be tiny, but 19th century experimental physics was becoming precise enough to look for it. In 1887, Albert Abraham Michelson and Edward Williams Morley carried out their famous experiment in Cleveland, Ohio. They used an instrument called an interferometer, designed to split a beam of light into two paths at right angles and then bring the beams back together. If Earth were moving through the ether, the two light beams should have taken slightly different amounts of time to complete their journeys. That difference would have shown up as a shift in the interference pattern, but the expected shift did not appear. The Michelson-Morley experiment did not, by itself, instantly create relativity or make every physicist throw their notebooks into the nearest bin. Science is usually less theatrical than that, which is probably best for the notebooks. But it became one of the key clues that something was wrong with the old picture. The expected evidence for Earth's motion through the ether was missing. Light did not seem to behave as though it were moving through a detectable universal medium. This left physics in an awkward position. Maxwell's electromagnetism had been brilliantly successful. The wave nature of light was well supported. But the assumed medium for those waves was becoming harder to defend. If light was an electromagnetic wave, but no motion through the ether could be detected, then perhaps the problem was not just with the ether. Perhaps the deeper issue was the old assumption that space and time formed a fixed background, against which all motion could be measured. Several scientists worked on this puzzle before Einstein's breakthrough. Hendrik Lorentz developed mathematical transformations that explained how measurements of space and time might change for moving systems. He proposed length contraction, the idea that objects moving through the ether might physically shorten along their direction of motion. Henri Poincaré also made important contributions, developing ideas about local time, transformations, and the principle of relativity. These ideas brought physics close to a new way of thinking, even though the older ether picture still lingered in the background. The strange lesson was becoming clearer. The speed of light did not behave like the speed of an ordinary object moving through ordinary space. A thrown stone has a speed that depends on the motion of the thrower and the observer. A train speed looks different to a passenger, a person on the platform, and a bird overhead with unusually strong opinions about railway timetables. Light seemed different. Its speed appeared to be built into the laws of electromagnetism themselves. That made light more than just another moving thing inside the universe. It became a clue about the structure of the universe. If the speed of light was fixed in a deep physical sense, then space and time could not both remain absolute in Newton's old way. Something had to adjust. Either the measurements of distance, the measurements of duration, or the meaning of simultaneity itself would have to change. Light had begun as a familiar part of the world. Sunshine, firelight, starlight, the soft glow of morning through a curtain. But inside its speed was a quiet challenge to classical reality. The old universe had treated space as a fixed stage and time as a universal clock. Light suggested that the stage and the clock were not as separate or as steady as they seemed. In 1905, Albert Einstein published a paper that quietly changed the meaning of space and time. It did not begin with a huge machine, a telescope pointed into the deep universe, or a dramatic explosion in a laboratory, which is always a little disappointing for anyone hoping physics would come with more smoke. It began with a problem about light, motion, and the rules that all observers should agree upon. Einstein's theory became known as special relativity. It is called special because it deals with a special case. Observers moving at constant speeds in straight lines without acceleration or gravity complicating the picture. Even within that limited setting, the result was extraordinary. Einstein rebuilt the old Newtonian understanding from two central ideas. The first was that the laws of physics are the same for all observers moving steadily. The second was that the speed of light in vacuum is the same for all such observers, no matter how they are moving. That second idea is where the universe begins to feel deeply strange. In everyday life, speeds add and subtract in simple ways. If a person throws a ball forward from a moving train, someone on the platform measures the ball's speed as the speed of the train plus the speed of the throw. If a person walks down the aisle of an aircraft, their speed relative to the ground includes the aircraft's motion. Common sense says motion should stack neatly like this. Light refuses to play along. According to special relativity, a beam of light in vacuum travels at the same speed for every observer in steady motion. Whether someone shines a torch from a spaceship moving toward you or away from you, the light itself is still measured to move at the same speed in vacuum. That speed is about 300,000 kilometers per second. It is not just very fast, it behaves like a fixed feature of physical law. This creates a serious problem for the old picture of separate space and time. If light speed is constant for different observers, then distance and duration cannot both remain fixed and universal. Speed is connected to how far something travels and how long it takes. So if the speed of light must stay the same, then measurements of space and measurements of time have to adjust. The universe keeps light consistent by making distance and duration more flexible than Newton had imagined. One result is time dilation. Time dilation means that a moving clock is measured to tick more slowly relative to an observer. This is not a trick of eyesight, a delay in signals, or a mistake caused by bad clockwork. It is a real physical effect built into the structure of space-time. Each observer experiences their own clock normally. A person travelling in a fast spacecraft would not feel their own heartbeat slowing, or their thoughts turning into syrup. But compared with someone who stayed behind, less time can pass for the traveller. A simple way to picture this is with a light clock. Imagine a pulse of light bouncing between two mirrors. Each bounce marks a tick. For someone beside the clock, the light moves straight up and down. For someone watching that same clock move past, the light follows a longer diagonal path between the mirrors. Because the speed of light remains the same, the longer path must take more time. The moving clock is therefore measured to tick more slowly. The clock is not broken. The observer is not confused. Space and time are adjusting together. Another result is length contraction. A moving object is measured as shorter along the direction of its motion. This does not mean the object feels squeezed in its own rest frame. A spacecraft travelling steadily would not notice its own hull being crushed, and the crew would not need to complain to the manufacturer about relativistic legroom. From the spacecraft's own point of view, its length is normal. But an observer watching it rush past at a speed close to the speed of light would measure it as shortened in the direction of travel. Length contraction becomes significant only at speeds close to the speed of light, which is why chairs, trains, bicycles, and mildly hurried pedestrians do not appear dramatically compressed. At ordinary speeds, the effect is far too tiny to notice. But in high-energy physics, where particles move at enormous fractions of light speed, relativity is not optional. It is part of the working description of nature. Special relativity also changes the meaning of simultaneity. In Newton's universe, if two distant events happened at the same time, that fact was true for everyone. Einstein showed that this is not always the case. Two events that seem simultaneous to one observer may not seem simultaneous to another observer moving differently. This does not mean cause and effect becomes chaotic. Events that can physically influence one another keep their causal order. But distant events with no possible signal connecting them can be sliced into space and time differently by different observers. A train thought experiment makes the idea gentler. Imagine flashes of light striking the front and back of a moving train. Someone standing on the platform may judge the flashes to happen at the same time, but someone inside the train is moving toward one flash and away from the other, so the light reaches them differently. Once the constant speed of light is taken seriously, the two observers can disagree about whether the flashes were simultaneous. Neither has made a mistake. They are measuring reality from different states of motion. This is the point where space and time can no longer remain separate in the old way. A measurement of distance depends on how time is being measured. A measurement of time depends on how motion through space is being described. Duration, length, simultaneity, and speed are tied together by the fixed speed of light. Special relativity did not say the world is unreal. It said the world is more carefully structured than common sense assumes. Space is still space. Time is still time. But they are no longer independent backgrounds. They behave like different aspects of one deeper physical arrangement, quietly waiting beneath every clock, every ruler, every beam of light, and every moving thing in the universe. Einstein had shown that space and time could no longer remain fully separate. Moving clocks ticked differently. Moving objects were measured differently. Events that seemed simultaneous to one observer might not be simultaneous to another. But the full meaning of this was not immediately obvious. Special relativity worked, and it worked beautifully, but it still needed a clearer shape in the imagination. That shape came from Hermann Minkowski. In 1908, Minkowski gave a famous lecture called Space and Time, in which he argued that Einstein's special relativity was best understood as a four-dimensional structure. Space by itself and time by itself, he suggested, were no longer the deepest description. The real physical structure was space-time. This was not just a new word placed neatly over old ideas, like putting a fresh label on a drawer and pretending the drawer is now tidy. It was a genuine change in how reality was described. Minkowski's space-time joins three dimensions of space with one dimension of time. The three spatial dimensions are the familiar ones: left and right, forward and backward, up and down. They describe where something is. The time dimension describes when something is. Together they allow every occurrence in the universe to be described not only by its location, but by its moment. A flash of lightning, the opening of a flower, the fall of a stone, the tick of a clock, and the arrival of a beam of starlight are all events in space-time. This does not mean time is simply another direction like north, east, or upward. That would be a tempting mistake, because four dimensions can sound like a larger version of ordinary space, but time behaves differently from space. A person can turn around and walk back across a room, but cannot casually turn around and stroll back into yesterday. Time has a different role in physics, especially in the ordering of cause and effect. Space-time unites space and time, but it does not make them identical in every ordinary sense. The key idea is that an event has both a where and a when. In everyday life, these are usually treated separately. A meeting has a location and a time. A sunrise has a place on Earth and a moment in the day. A supernova has a position in the sky and a point in cosmic history. In space-time, these are not two unrelated facts. They are parts of one complete description. Reality becomes less like a stage with a separate clock hanging above it, and more like a connected map of happenings. This map is not easy to picture, because human brains are very comfortable with three-dimensional space, and much less comfortable with four-dimensional anything. A useful analogy is a landscape viewed from different angles. Two people looking at the same valley from different hills may describe it differently. One sees a ridge stretching across the horizon, another sees the slope running away into the distance. Neither person has invented a false valley. They are seeing the same place from different perspectives. In special relativity, observers moving differently can describe the same space-time in different ways. One observer may divide events into space and time one way. Another observer, moving at a different steady speed, may divide them another way. They may disagree about the distance between events, the duration between events, and whether distant events happened at the same time. But they are not each living in a separate universe. They are making different measurements of the same underlying space-time. This is where the space-time interval becomes important. The space-time interval is the deeper relationship between events that remains consistent even when observers disagree about space and time separately. One observer might measure more distance and less time between two events. Another might measure less distance and more time, but the underlying space-time relationship is preserved. The separate ingredients can shift, while the combined structure remains stable. A gentle way to imagine this is to think of rotating a map on a table. The north-south and east-west measurements of a route may look different depending on how the map is turned relative to you, but the actual route has not changed. The analogy is limited, because space-time is not just a flat paper map, and time is not exactly like another direction across a page. Still, it gives a useful hint. Changing perspective can change how components are measured without changing the deeper thing being measured. This also helps explain the relativity of simultaneity. If observers slice space-time differently into space and time, then they can disagree about which distant events belong to the same present moment. One observer's slice of now across the universe may not match another observer's slice of now. This sounds unsettling, because daily life depends on a strong feeling that the present is universal. But special relativity shows that nature does not provide one cosmic present shared by all observers in all states of motion. The birth of space-time made Einstein's theory feel less like a collection of strange effects and more like a single geometric idea. Time dilation, length contraction, and the relativity of simultaneity were not separate tricks. They were different ways the same four-dimensional structure appeared to observers moving differently. So the title begins to take its proper shape. Space and time are not the same as human experiences. Distance still feels different from duration. A ruler still does a different job from a clock. But in modern physics, they are inseparable parts of one physical geometry. The universe is not built from space with time flowing beside it. It is built, at least in relativity, from space-time. Time dilation sounds like the sort of idea that should belong safely inside science fiction, preferably somewhere near a silver spaceship and a slightly suspicious glowing doorway. But in modern physics, it is not fiction at all. It is a measured, reliable effect, and it follows from one of the simplest and strangest facts in special relativity. All observers moving steadily measure light in vacuum at the same speed. That is the awkward little truth that keeps rearranging everything. If one observer is standing still on Earth and another is flying past in a spacecraft, both measure a beam of light in vacuum moving at about 300,000 kilometers per second. The spacecraft does not add its motion to the light in the ordinary way. The light does not politely speed up or slow down to match common sense. Instead, the speed of light remains fixed, and space and time adjust around it. A useful way to see this is with a light clock. Imagine a very simple clock made from two mirrors, one above the other, with a pulse of light bouncing between them. Each time the light travels from one mirror to the other, the clock ticks. For someone travelling with the clock, the light moves straight up and down. The distance is simple. The tick is normal. Nothing strange seems to be happening from that person's point of view. Now imagine watching that same light clock as it moves past you at high speed. From your perspective, the mirrors are not sitting still. They are sliding sideways as the light travels between them, so the light does not appear to move straight up and down. It follows a longer diagonal path. The light has farther to travel between ticks. Here is the important part. The light cannot simply move faster to cover that longer path. The speed of a light in vacuum stays the same. So if the path is longer and the speed is unchanged, the tick must take more time. From your frame of reference, the moving clock runs slow. This is time dilation. A moving clock is measured to tick more slowly relative to an observer. It is not caused by mechanical strain, poor engineering, or a clock having a dramatic personal crisis. It is not just what the observer sees after light has taken time to arrive. It is a real difference in how time is measured between frames of reference. Each observer still experiences their own time normally. This personal time is called proper time. Proper time is the time measured by a clock travelling along with you. If you were inside the spacecraft, your watch would tick normally. Your thoughts would feel normal. Your cup of tea would cool at its usual disappointing pace. From your own point of view, you would not feel time becoming slow. The difference appears when comparing your clock with another clock moving differently. This is one reason relativity can feel so slippery at first. Everyone carries their own normal experience of time. No observer feels broken. No clock in its own frame feels wrong. But when two observers move relative to one another and later compare measurements, they may find that different amounts of time have passed. The universe allows each local experience to feel ordinary, while the comparison between experiences reveals something extraordinary. This effect has been tested in the real world. One famous example comes from muons, unstable particles created when high-energy cosmic rays strike particles in Earth's upper atmosphere. Muons decay very quickly. In a purely classical picture, many of them should vanish before reaching the ground. Yet large numbers are detected at Earth's surface. Special relativity explains why. From Earth's frame of reference, the muons are moving so fast that their internal clocks are time dilated, allowing them to survive longer than classical expectations would predict. From the muon's own point of view, the explanation can be described differently. Its own lifetime is normal, but the distance through Earth's atmosphere is length contracted. This is beautifully strange because both descriptions are valid. One observer emphasizes stretched time, the other emphasizes shortened distance. The same physical event is being sliced into space and time in different ways. Another important test came from the Hafele-Keating experiment in the early 1970s. Physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial aircraft and compared them with atomic clocks that stayed on the ground. The clocks did not perfectly agree afterward. The differences were tiny, measured in billionths of a second, but they matched the combined predictions of special relativity and general relativity. Motion affected the clocks, and so did their different positions in Earth's gravitational field. That may sound like a small effect, and in daily life it is. Nobody boards a plane and returns dramatically younger, unless the flight was especially relaxing and the airport lighting was unusually kind. But the principle is enormous. Time is not detached from motion through space. How fast something moves affects how duration is measured. This points directly back to the deep connection between space and time. In the older Newtonian picture, motion happened through space while time flowed independently in the background. In special relativity, that separation no longer holds. Motion through space changes the measurement of time. A path through the universe is not just a path across distance. It is a path through space-time, where distance and duration are linked by the fixed speed of light. Time still feels steady because human life unfolds at slow speeds compared with light. But beneath that familiar steadiness, Every clock carries a quiet relationship with motion. The faster paths through space become, the more clearly time reveals that it was never standing apart from space at all. Time is not the only thing that changes when motion becomes extreme. Distance changes too. This is the partner effect to time dilation, and it is called length contraction. If time dilation shows that moving clocks are measured differently, length contraction shows that moving rulers are measured differently. The two effects are not separate oddities placed into physics for decorative confusion. They belong together because space and time are joined inside the same structure. Length contraction means that an object moving relative to an observer is measured as shorter along the direction of its motion. That last part matters. The contraction is not in every direction at once. A fast spacecraft is not measured as shrinking equally like a balloon losing air. Its length changes only along the line of travel. If it is moving nose first through space, then its nose-to-tail length is measured as shorter by an outside observer, while its height and width are not contracted in the same way. This effect is far too small to notice at everyday speeds. A car driving along a road is technically length contracted by an absurdly tiny amount. But no one needs to worry that the family hatchback has become physically suspicious on the motorway. Even a jet aircraft moves far too slowly compared with a light for the effect to matter in ordinary experience. Length contraction becomes important only when objects travel at speeds close to the speed of light, where relativity stops whispering politely and begins to speak clearly. A spacecraft example helps make the idea more comfortable. Imagine a spacecraft travelling from Earth toward a nearby star at an enormous fraction of the speed of light. To observers who remain near Earth, the star is several light years away, and the spacecraft takes a certain amount of Earth-measured time to get there. Those observers measure the journey across a large interstellar distance. Their clocks and rulers belong to their frame of reference, but to the travellers inside the spacecraft the situation can be described differently. Their own clocks tick normally for them. Their own spacecraft feels unchanged. They do not feel pressed shorter, and they do not see their cabin politely folding itself into a cupboard. Instead, from their frame of reference, the distance to the star is contracted. The gap between the starting point and destination is measured as shorter along the direction of travel. Less proper time passes for the travellers, and the distance they measure across space is reduced. This is one of the most elegant parts of special relativity. The same journey can be described through time dilation from one frame and length contraction from another. Earth observers say the fast-moving travellers' clocks run slow. The travellers say the distance ahead has shortened. Both descriptions are valid within their own frames of reference. They are different slices through the same space-time reality. Length contraction also connects deeply with the relativity of simultaneity. Measuring the length of a moving object is not as simple as it first seems. To measure the length of something, an observer must determine where both ends are at the same time. For an object at rest, that sounds straightforward. But for a moving object, the phrase "at the same time" becomes more complicated. Special relativity shows that observers moving differently can disagree about whether two distant events are simultaneous. So when one observer measures both ends of a moving spacecraft at one moment in their frame, another observer does not necessarily agree that those two end measurements happened at the same time. This is why length contraction is not merely a visual effect. It is not just what something looks like after light has taken time to reach the eye or a camera. Actual appearances can involve additional complications because light from different parts of an object arrives at different times. Length contraction is deeper than appearance. It is a statement about measurements of space in a particular frame of reference. It follows from the geometry of space-time itself. In high-speed particle physics, this matters. Particles in accelerators can move at speeds extremely close to the speed of light. Their behavior cannot be accurately described using only Newtonian space and time. Relativistic effects shape how their lifetimes, energies, paths, and interactions are understood. The European Organisation for Nuclear Research, better known as CERN, works with particles moving so fast that relativity is part of the basic language of the experiment. In that realm, length contraction and time dilation are not philosophical curiosities, they are working physics. The deeper lesson is that space is not a fixed background that stays unchanged while time alone becomes flexible. Motion affects the measurement of both. When an object moves rapidly through space, observers disagree not only about how much time passes, but also about how much distance is involved. The old Newtonian picture treated distance and duration as independent quantities, measured against absolute space and absolute time. Special relativity replaces that with a more subtle view, where space and time depend on the observer's motion, but space-time remains consistent underneath. So distance changes too, not because reality is flimsy, but because reality is structured more deeply than everyday intuition suggests. Space does not sit apart from time, holding perfectly still while clocks do strange things nearby. A ruler and a clock are linked. Motion through space changes measurements of time, and motion through time changes how space is divided. The universe is not keeping distance in one box and duration in another. It is holding them together in space-time, where every journey is measured not only by how far it goes, but by how it moves through the joined fabric of space and time. Light does not only change how space and time are measured, it also helps decide what can touch what can influence what, and what can never be connected at all. This is where the idea of a light cone becomes important. A light cone is not a glowing object floating somewhere in space, sadly, because that would make relativity much easier to decorate. It is a way of describing the structure of cause and effect in space-time. Every event in the universe has a location and a time. A match is struck, a star explodes, a message is sent from a spacecraft, a photon leaves the surface of the sun. Each of these is an event in space-time. From any event, light can spread outward in all directions. As time passes, that expanding sphere of light reaches farther and farther away. If this spreading light is drawn on a space-time diagram, with time running upward and space shown sideways, the path of the light forms a cone shape. That shape is called a light cone. The light cone separates what can be influenced from what cannot. Because nothing carrying information can travel faster than light in vacuum, an event can only affect things inside its future light cone. That future light cone contains all the places and times that light, particles, messages, gravity changes, or any physical influence from that event could possibly reach. Outside that region, the event cannot have an effect because reaching it would require something to outrun light. There is also a past light cone. This contains all the events that could have influenced the event being considered. If a signal, a particle, a beam of light, or a gravitational effect could have reached the event from somewhere else, then that earlier event lies inside its past light cone. The past light cone is like the record of what could have helped shape the present moment. The future light cone is the region the event may go on to shape. This turns the speed of light into something deeper than a fast number. It is not merely a speed limit painted on the road of the universe, with nature acting as a very stern cosmic traffic officer. It is part of the architecture of causality itself. It tells space-time which events can be connected by physical influence and which cannot. Cause and effect are not floating loosely through the cosmos. They are organized by the structure of space-time. Physicists describe relationships between events in three broad ways. Time-like separation means two events are close enough in space and far enough apart in time that something moving slower than light could travel from one to the other. A person growing older, a spacecraft travelling from one planet to another, or a clock ticking from one moment to the next, follows a time-like path. These events can be causally connected in an ordinary physical way. Light-like separation means the only thing that could connect two events is something moving exactly at the speed of light in vacuum. A photon leaving the sun and later reaching Earth follows this kind of relationship. Sunlight takes a little over 8 minutes to travel from the sun to Earth, So the sunlight arriving now began its journey several minutes ago. The sun seen in the sky is not the sun of the exact present moment on Earth. It is the sun as light has delivered it, with a short but real delay. Space-like separation means two events are too far apart in space and too close together in time for even light to travel between them. No signal, message, particle or physical influence can connect those events directly. Observers moving differently may disagree about which of two space-like separated events happened first. They may even disagree about whether the events were simultaneous. But because neither event can influence the other, this disagreement does not break cause and effect. That is one of the most careful balances in special relativity. Different observers can disagree about simultaneity, but they cannot disagree about the causal order of events that can physically affect one another. If one event sends a signal that reaches another, all observers agree that the sending happens before the receiving. The timing measurements may differ, the distances may differ, the descriptions may be sliced differently into space and time, but cause still comes before effect where cause and effect are physically connected. This is why light cones matter so much. They protect causality while allowing space and time to be flexible. They explain how the universe can let observers disagree about distant, unconnected events without letting reality collapse into nonsense. Relativity is strange, but it is not chaos. It is an extremely precise way of saying which measurements depend on the observer and which relationships remain physically fixed. The same idea appears across astronomy. When light from a nearby star reaches Earth, it may have travelled for years. When telescopes observe a distant galaxy, they may be seeing light that began its journey millions or even billions of years ago. The farther away an object is, the further back in time its light usually shows it. Astronomy is therefore not only the study of distant places, it is also the study of earlier times, because light carries the past across space. Messages crossing space obey the same rule. A radio signal sent to Mars cannot arrive instantly. Depending on where Earth and Mars are in their orbits, the delay can range from several minutes to more than 20 minutes. Space agencies such as NASA and the European Space Agency must work with these delays when communicating with spacecraft and rovers. There is no way to simply shout across spacetime faster than light, however tempting that might be when a robot is slowly deciding whether to drive around a rock. Light cones show that spacetime is not just a convenient way to combine rulers and clocks. It is a structure that decides which events can be linked by physical influence. Space and time together shape the possible paths of signals, particles, light and information. They form the hidden geometry behind every cause and every effect. So the unity of space and time is not only about how observers measure distance and duration, it is also about how reality connects itself. Every event opens into a future it can influence, and rests inside a past that could have influenced it. Between these regions lies the quiet order of space-time, holding the universe together with the speed of light as its boundary, kept close to the 800-word target. Gravity is the idea that seems most naturally like a force. A ball falls because gravity pulls it down. The moon stays near Earth because Earth's gravity pulls on it. Earth stays in orbit around the Sun because the Sun's gravity reaches across space and holds it in a great curving path. This way of speaking is useful, familiar, and in many situations accurate enough to build bridges, land spacecraft, and stop cups of tea from floating away in an unnecessarily dramatic fashion. But Einstein's general relativity changed the deeper meaning of gravity. In 1915, Albert Einstein completed the theory of general relativity. Special relativity had dealt with observers moving steadily, without acceleration or gravity. General relativity went further. It asked what happens when motion is not steady, when objects accelerate, and when gravity enters the story. The result was one of the most profound changes in physics. Gravity was no longer described as a force pulling objects through a fixed background of space and time. Instead, Gravity became geometry. The key idea that guided Einstein was the equivalence principle. This principle says that the effects of gravity and acceleration can be locally indistinguishable. Imagine standing inside a closed elevator. If the elevator is resting on Earth, the floor pushes upward on your feet and you feel your weight. Now imagine the elevator far out in empty space, away from planets and stars, accelerating upward. The floor would also push against your feet. Inside the elevator, without looking outside, it could feel very much like gravity. The opposite is also true. If the elevator were falling freely near Earth, you would feel weightless inside it, at least until the experiment became extremely unpopular with the building manager. A falling object is still under the influence of Earth's gravity, but because everything nearby is falling together, there is no ordinary feeling of weight. Astronauts in orbit experience something similar. They are not beyond Earth's gravity. They are continuously falling around Earth, following a curved path that never quite meets the ground. Einstein realized that this connection between gravity, acceleration, and free fall was not a small technical detail. It was a clue to the structure of reality. If gravity could disappear locally for a freely falling observer, then perhaps gravity was not a force in the ordinary Newtonian sense. Perhaps objects in free fall were not being pulled away from their natural paths. Perhaps they were following the natural paths available to them. General relativity describes these natural paths as geodesics. A geodesic is the straightest possible path through curved space-time. On the curved surface of Earth, the shortest route between two distant points is not usually a straight line on a flat map, but a great circle across the globe. In a similar spirit, though, with much deeper mathematics, objects in curved space-time follow geodesics. A planet orbiting the Sun is not being tugged by an invisible thread through empty space. It is moving along a natural path through space-time shaped by the Sun's mass and energy. This required mathematics capable of describing curved spaces. One of the important figures behind that mathematical foundation was Bernhard Riemann, a 19th century mathematician whose work on geometry helped make it possible to describe spaces that are not flat. The field known as differential geometry gave physicists the language needed to talk about curvature precisely. Einstein did not simply add a poetic metaphor to gravity. He built a physical theory in which the shape of space-time could be calculated and tested. In general relativity, mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. That sentence is often used because it captures the heart of the theory beautifully. The Sun changes the geometry around it. Earth moves through that geometry. Light passing near the Sun follows a path affected by that curvature. Time itself is also altered, ticking at different rates in different gravitational conditions. This is where the unity of space and time becomes deeper than it was in special relativity. Special relativity showed that space and time are linked by motion and the constant speed of light. General relativity shows that space-time is not merely a fixed structure waiting in the background. It is flexible. It responds. It bends and stretches according to the presence of mass and energy. The stage has become part of the performance. This does not mean Newton's description becomes useless. For weak gravity and low speeds, Newtonian gravity remains extremely accurate. It is still used in engineering, astronomy, navigation, and everyday calculations. But general relativity explains why Newton's picture works so well in ordinary conditions, while revealing what gravity really seems to be at a deeper level. Gravity is not simply a pull across space, it is the behavior of space and time together. That brings the title into its strongest form. Space and time are not the same thing in the ordinary everyday sense. A clock is still not a ruler, a second is still not a meter. But in the physical structure described by relativity, space and time are inseparable parts of one fabric. Gravity alters both together. Mass changes the shape of space, but it also changes the rate at which time passes. A planet, a star, a falling stone, and a beam of light are all responding to the same curved space-time geometry. The universe is therefore not a collection of objects moving through an untouched emptiness, while time ticks separately above them. Matter and energy shape spacetime, and spacetime shapes the motion of matter and energy. Gravity becomes the moment where the old separation finally gives way. Space and time are not only joined, they are active, responsive, and woven into the structure of reality itself. Gravity does not only curve paths through space, it changes time itself. That may sound like the sort of sentence that should be whispered beside a black hole, preferably while a dramatic orchestra becomes concerned in the background. But gravitational time dilation is not only a deep space spectacle, it is a real, measured effect, and it happens here, around Earth, in the quiet background of ordinary life. Gravitational time dilation means that clocks deeper in a gravitational field tick more slowly compared with clocks farther away. Near a massive object, space-time is curved more strongly. Farther from that object, the curvature is weaker. In general relativity, this difference affects the rate at which time passes. A clock closer to a planet, star, or black hole is not merely seen to run slowly because its light takes time to reach someone else. It actually measures less elapsed time compared with a clock higher up in the gravitational field. Earth provides a gentle example. A clock at sea level is slightly deeper in Earth's gravitational field than a clock on top of a mountain. According to general relativity, the sea level clock ticks extremely slightly more slowly. The difference is tiny, so tiny that no one walks down from a hill with noticeably more personal history than someone who stayed by the beach. A human lifetime is not dramatically altered by taking the stairs, but with precise enough instruments, the effect is real. Modern atomic clocks are accurate enough to measure these tiny differences. Atomic clocks use the regular behavior of atoms, often cesium or optical transitions in other atoms and ions, to measure time with extraordinary precision. Experiments have shown gravitational time dilation over height differences small enough to fit inside laboratories. In modern precision timekeeping, moving a clock upward by a small amount can measurably change how quickly it ticks compared with a clock lower down. Time is not an abstract river flowing evenly everywhere. It has a relationship with gravity. This is one of the calmest and strangest lessons in all of relativity. The floor beneath your feet is at a slightly different gravitational potential from the roof above you. The effect is almost impossibly small in daily life, but it is not imaginary. Time at your feet ticks very slightly more slowly than time near your head, simply because your feet are closer to Earth's mass. This is not usually a practical concern unless one is a clock of exceptional sensitivity, in which case life must be a constant emotional strain. The global positioning system depends on this kind of physics. The satellites used for navigation carry precise clocks, and those clocks do not tick at exactly the same rate as clocks on Earth's surface. Two relativistic effects matter. Special relativity says that because the satellites are moving relative to the ground, their clocks are affected by motion and tend to tick more slowly from the ground-based perspective. General relativity says that because the satellites are higher in Earth's gravitational field, where gravity is weaker, their clocks tick faster than comparable clocks on the ground. The total correction is essential. If the global positioning system ignored relativity, the timing errors would build up quickly, and position estimates would drift by significant distances. Satellite navigation works because engineers account for the fact that time does not pass at exactly the same rate everywhere around Earth. Every time a phone, aircraft, ship, or mapping system uses satellite timing to estimate location, it is quietly relying on Einstein's physics. General relativity is not only sitting in a textbook looking elegant, it is helping people find coffee shops, airports, mountain trails, and occasionally the wrong car park with great confidence. This is why gravity-changing time should not be treated as only a black hole effect. Black holes show the effect in extreme form, because their gravitational fields can be intense enough to bend space-time dramatically. Near an event horizon, the difference between time for a distant observer and time closer to the black hole can become enormous. But the same principle exists in weaker form around Earth, the Moon, the Sun, and every mass in the universe. Wherever gravity exists, spacetime is shaped, and time is part of what changes. In Newton's view, gravity pulled objects through space while time flowed evenly in the background. General relativity replaces that picture with something deeper. Mass and energy shape space-time, and that shaping affects both the paths objects follow and the rates clocks measure. Gravity is not only about where objects go, it is also about how long their journeys take, how clocks compare, and how different regions of the universe keep time. This brings the unity of space and time into sharper focus. If gravity only bent paths through space, then perhaps space and time could still be imagined as separate companions. But gravity changes the flow of time as well. The same mass that curves the path of a planet also changes the rate of a clock. The same space-time geometry that guides falling objects also determines how duration is measured. Space and time are therefore linked not only by motion but by gravity itself. A mountain summit, a satellite orbit, a sea-level laboratory, and the region near a star all belong to the same curved space-time structure. Their distances and durations cannot be fully separated. Gravity reveals that time is woven into the physical fabric of the universe, not floating above it as an independent cosmic clock. Mass slows time because mass shapes space-time, and once that is understood, the old idea of space as a stage and time as a separate ticking background becomes much harder to hold. The universe is stranger and more unified than that. Every clock is somewhere, every somewhere has gravity. And every measurement of time belongs to the geometry of space-time. Curved space-time sounds like a beautiful idea, but physics cannot survive on beauty alone. A theory has to face the universe and let the universe answer back. General relativity did not become powerful simply because it was elegant. It became powerful because it explained things that could actually be measured. One of the first great tests involved the planet Mercury. Mercury is the closest planet to the Sun, so it moves through the strongest solar gravity of all the major planets. Its orbit is not a perfect circle. Like the other planets, it follows an ellipse, a slightly stretched path around the Sun. The point where Mercury comes closest to the Sun is called its perihelion. Over time, this closest point slowly shifts around the Sun. This shifting is known as precession. Most of Mercury's perihelion precession could be explained using Newtonian gravity. The gravitational pulls of Venus, Earth, Jupiter, and the other planets all tug slightly on Mercury's orbit, changing it over time. But once astronomers accounted for all the known Newtonian effects, there was still a small extra shift left over. It was not large. It was about 43 seconds of arc per century, a tiny angle spread across 100 years. But in astronomy, small leftovers can become very loud. This unexplained motion had bothered scientists for decades. Some suggested there might be another planet inside Mercury's orbit, sometimes called Vulcan, whose gravity could account for the missing shift. Searches were made, claims appeared, and the imaginary planet had a reasonably dramatic career for something that did not exist. But Vulcan was never confirmed. The puzzle remained. Einstein's general relativity accounted for the extra shift naturally. Near the Sun, space-time is slightly curved by the Sun's mass. Mercury is not simply being pulled through flat space by a force. It is following a path through curved space-time. When the mathematics of general relativity is applied to Mercury's orbit, the extra perihelion precession appears without needing an unseen planet. This was one of the first major successes of Einstein's theory, and it showed that curved space-time was not just an abstract idea. It changed the motion of a real planet. Another prediction involved light. If mass curves space-time, then light should also follow curved paths near massive objects. This was a striking idea because light has no rest mass, so in the older Newtonian picture, its behaviour near gravity was not as straightforward. In general relativity, the issue becomes clearer. Light follows the geometry of space-time. If space-time is curved near the Sun, then starlight passing close to the Sun should appear slightly deflected. Testing this required observing stars whose apparent positions lay close to the sun in the sky. Usually, the sun's glare makes this impossible, because the daytime sky is not exactly kind to delicate starlight. A total solar eclipse offers a rare opportunity. When the moon covers the sun, stars near the sun's apparent position can be photographed and compared with their positions when the sun is elsewhere in the sky. In 1919, Arthur Eddington helped lead eclipse expeditions to test Einstein's prediction. Observations were made from Príncipe, off the west coast of Africa, and from Sobral in Brazil. The results supported the bending of starlight predicted by general relativity and helped make Einstein internationally famous. The historical moment was important, but it is also worth being careful. The 1919 data were difficult, affected by weather and observational limitations, and later measurements became far more precise. The eclipse expedition was a dramatic early confirmation, not the final word carved into the heavens with a cosmic fountain pen. Modern astronomy has confirmed gravitational light bending far more extensively. Gravitational lensing is now a major tool in astrophysics. When light from a distant galaxy passes near a massive galaxy or galaxy cluster, the intervening mass can bend and magnify that light. Sometimes the background galaxy appears distorted into arcs, rings, or multiple images. These effects have been observed by telescopes operated by the National Aeronautics and Space Administration, the European Space Agency, and many ground-based observatories. Gravitational lensing allows astronomers to study distant galaxies, measure the distribution of dark matter in galaxy clusters, and examine the large-scale structure of the universe. It is one of the clearest demonstrations that mass changes the paths taken by light. Space is not merely an empty container. Its geometry matters. This connects directly with the earlier idea that gravity changes time. Around a massive object like the Sun, space-time is altered. Mercury's orbit changes because the geometry near the Sun is not exactly Newtonian. Starlight bends because light follows paths through that same curved geometry. Clocks tick differently in different gravitational conditions because time is part of the geometry too. The significance is calm but enormous. Planets, light, and time are not responding to three separate hidden mechanisms. They're responding to one space-time structure. A planet's orbit, a beam of starlight, and the rate of a clock all reveal different aspects of the same underlying geometry. That is why the first tests of general relativity mattered so much. They showed that curved space-time could be observed through real changes in the universe. Mercury's slow orbital shift and the bending of starlight near the Sun were not decorative details. They were signs that space and time had to be understood together. When gravity acts, it does not only tug objects, it reshapes the geometry in which motion, light and time all unfold. Black holes are where the idea of space-time stops being gentle and begins to show its most extreme face. They're not simply heavy objects with very strong gravity, though that is often the first way they are imagined. A black hole is a region where space-time curvature becomes so intense that an event horizon forms. Beyond that boundary, light cannot escape to distant observers. If light cannot get out, then no ordinary signal, message, particle, or dramatic complaint from the darkness can get out either. This makes a black hole very different from a planet or a star. A planet has a surface. A star has glowing layers of gas and plasma. An event horizon is not a solid shell. It is not a wall someone would crash into like a cosmic window. It is a boundary in space-time, defined by the future paths available to light and matter. Outside the event horizon, there are paths that can still lead away. Inside it, all future paths point deeper inward. Escape is not merely difficult. According to classical general relativity, it is no longer part of the available geometry. The first exact mathematical description of this kind of object appeared surprisingly soon after Einstein completed general relativity. In 1916, Karl Schwarzschild found a solution to Einstein's field equations, for the space-time around a non-rotating spherical mass. This became known as the Schwarzschild solution. It led to the idea of the Schwarzschild radius, the distance from the centre of a mass at which the escape boundary would form if that mass were compressed tightly enough. For the Sun, the Schwarzschild radius would be only a few kilometres. That does not mean the Sun is a black hole, because the Sun is vastly larger than that, and its mass is spread across a huge glowing sphere. But if the same mass were somehow compressed inside that small radius, an event horizon would form. For Earth, the corresponding radius would be less than a centimetre. This gives a sense of how extreme black holes are. They are not merely massive, they are masses compressed into regions where space-time becomes profoundly curved. Near a black hole, gravitational time dilation becomes dramatic. To a distant observer watching something fall toward the event horizon, the falling object appears to slow down as it approaches. Its light becomes stretched to longer wavelengths, becoming dimmer and redder. In that distant view, the object seems to fade near the boundary, never quite crossing in any simple visible way. This is not because the falling object has stopped experiencing time, it is because light escaping from near the event horizon struggles through severely curved space-time. For the infalling observer, the experience is different. In a sufficiently large black hole, crossing the event horizon might not feel like hitting a surface at all. Their own clock continues ticking normally from their point of view. They pass inward, unaware of any local sign that says, with great cosmic politeness, that return is no longer possible. The difference between the distant observer's description and the falling observer's description is one of the strangest features of black holes, and it shows how deeply time depends on position and motion in curved space-time. At the centre of a classical black hole, general relativity predicts a singularity. A singularity is often described as a point where density and curvature become infinite. But this should be treated carefully. Most physicists do not see singularities as a complete physical description of nature. Instead, they are usually taken as signs that classical general relativity has reached its limit. When curvature becomes extreme enough, quantum physics is expected to matter, and a deeper theory of quantum gravity may be needed. The singularity is less like a finished answer, and more like a signpost saying, very quietly, that the current map has run out. Roger Penrose made crucial contributions to understanding gravitational collapse and singularity theorems, showing that singularities were not just oddities of perfectly neat mathematical examples. Under broad conditions, general relativity seemed to predict them as a real consequence of collapse. Stephen Hawking later extended this kind of thinking into cosmology and black hole physics, and he also showed that black holes are not entirely black when quantum effects are considered. Hawking radiation suggests that black holes can emit a faint thermal glow and slowly lose mass over immense timescales, although this effect is far too weak to observe from ordinary astrophysical black holes with current technology. Black holes connect directly to the idea that space and time are not separate backgrounds. They are not ordinary objects sitting inside ordinary space while ordinary time flows nearby. A black hole is a place where the structure of space-time itself becomes the main feature. The event horizon is a boundary created by space-time geometry. The slowing of distant clocks is a change in time caused by gravity. The inward paths beyond the horizon are paths shaped by curved space-time, not by a simple pull through empty space. This is why black holes are so important to the meaning of relativity. They turn abstract ideas into something almost physical enough to feel. Space bends so severely that all future directions lead inward. Time stretches differently for observers depending on where they are and how they move. Light, the fastest messenger in the universe, finds itself trapped by geometry. In everyday life, space and time seem calm and separate. Around a black hole, that calm separation disappears. Space tells time how to behave. Time helps define what directions are available. The future itself becomes shaped by gravity. A black hole is not just a dark object in the universe. It is a region where space-time reveals how powerful, active, and deeply unified it really is. If black holes show spacetime at its most extreme, gravitational waves show that spacetime can move. A gravitational wave is a ripple in spacetime produced when massive objects accelerate in certain ways. The strongest waves come from some of the most violent events in the universe, especially pairs of black holes or neutron stars spiraling together before merging. These objects are incredibly dense, incredibly compact, and incredibly good at making ordinary human ideas about quietness feel a little underprepared. Einstein's general relativity predicted gravitational waves in 1916. The idea followed naturally from the theory. If mass and energy shape space-time, and if massive objects move and accelerate, then disturbances in that geometry should be able to travel outward. In a very loose comparison, a stone dropped into a pond sends ripples across the water. But gravitational waves are not ripples in a substance inside space. They are ripples of space-time itself, spreading at the speed of light. The problem was that these ripples are astonishingly weak by the time they reach Earth. Even a collision between two black holes can pass through this planet and change distances by less than the width of a proton across an instrument several kilometers long. That is not merely a small measurement. That is the universe asking scientists to detect a whisper from across cosmic history while standing next to all the noise of Earth. It is a beautifully unreasonable request, and naturally, physicists accepted. One of the early figures in the search was Joseph Weber. In the 1960s, Weber built large aluminium bars designed to vibrate if a gravitational wave passed through them. His claimed detections were not confirmed by later experiments, and his results remain controversial, but his work helped begin the experimental hunt. The search for gravitational waves required not only imagination, but instruments of extraordinary sensitivity. The later breakthrough came through laser interferometers. These instruments send laser beams along long arms and then bring the light back together. If a gravitational wave passes through, it should stretch space slightly in one direction and squeeze it slightly in another, changing the relative lengths of the arms by an incredibly tiny amount. The effect is so small that the detectors must account for ground vibrations, thermal noise, passing vehicles, and all the small disturbances of a planet that absolutely refuses to sit still. The most famous of these instruments is the Laser Interferometer Gravitational Wave Observatory, known as LIGO. Its detectors in the United States work with the LIGO Scientific Collaboration, and with other observatories around the world, including Virgo in Europe and Kagra in Japan. Together, these instruments form a global network, allowing scientists to confirm signals and estimate where in the sky the waves came from. The first direct detection came in 2015. The signal was produced by two black holes merging more than 1 billion light-years away. As they spiraled together, they released an enormous amount of energy in gravitational waves. By the time the waves reached Earth, the effect was tiny, but LIGO detected the brief stretching and squeezing of space-time. The signal lasted only a fraction of a second, but it carried news from one of the most extreme events in the universe. This detection was a landmark because it confirmed that space-time is not simply a passive stage. It is dynamic. It can bend, stretch, squeeze, ripple, and carry energy. General relativity had already shown that space-time guides planets, bends light, and changes the rate of clocks. Gravitational waves added something even more direct. Space-time itself can transmit disturbances across the universe. These waves also give scientists a new way to study black holes and neutron stars. Ordinary telescopes rely on light, radio waves, X-rays, and other forms of electromagnetic radiation. Gravitational wave astronomy listens to the motion of space-time itself. It can detect events that may be dark or difficult to observe with light alone. When neutron stars merge, gravitational waves can be combined with telescope observations, creating what scientists call multi-messenger astronomy. In 2017, such an event was observed through both gravitational waves and light, giving researchers a richer view of the collision. The connection to black holes is especially powerful. Black holes are difficult to study because their event horizons do not let light escape. But when two black holes orbit each other and merge, the changing curvature of space-time produces gravitational waves. The waves carry information about the masses, spins, and final merged object. In this way, some of the strongest evidence for extreme space-time comes from the final moments of massive compact objects spiraling together. Gravitational waves make the unity of space and time feel almost tangible. If space and time were merely a background, there would be nothing to ripple. If gravity were only an invisible pull through fixed space, merging black holes would not send waves of geometry across the cosmos. But in general relativity, the fabric itself responds. It changes shape and those changes travel. So space-time is not only where events happen, it participates. It curves around stars, slows clocks near mass, traps light around black holes, and trembles when dense objects collide. The universe is not a performance on a silent stage. The stage itself can move, and when it does, it carries the memory of cosmic violence across billions of light years, arriving at Earth as a faint stretch, a faint squeeze, and a quiet confirmation that space and time are woven into one living geometry. General relativity does not stop at planets, stars, clocks, and black holes. It can also be applied to the universe as a whole. That wider use of general relativity is called cosmology, the study of the large-scale structure, history, and evolution of the universe. Instead of asking how one planet moves around one star, cosmology asks a much larger question. What does space-time itself do when the entire universe is considered at once? This is where the idea becomes quietly enormous. If gravity is the curvature of space-time, and if space-time responds to mass and energy, then the universe cannot be understood as a collection of galaxies sitting inside a fixed, unchanging emptiness. The large-scale universe has its own geometry. It has a history. It can expand, evolve, and change over cosmic time. Soon after Einstein completed general relativity, some scientists began exploring what the theory implied for the universe as a whole. Alexander Friedmann, a Russian mathematician and physicist, found solutions to Einstein's equations in the early 1920s, showing that the universe did not have to be static. It could expand or contract. This was a bold result because the common expectation at the time was that the universe was eternal, fixed, and broadly unchanging on the larger scales. Georges Lemaitre, a Belgian priest and physicist, independently developed similar ideas and connected them with observations of distant galaxies. Lemaitre proposed that the universe was expanding and even suggested that it had evolved from a much denser earlier state. This was long before the modern Big Bang model became widely accepted. It was a remarkable insight. General relativity did not merely describe objects moving through space-time, it could describe space-time itself changing. Observational evidence came through the work of Edwin Hubble and others studying distant galaxies. In the late 1920s, Hubble showed that many galaxies outside the Milky Way appear to be receding from us, and that more distant galaxies generally showed greater recession. This relationship became a key clue that the universe is expanding. The light from distant galaxies is stretched toward longer wavelengths, a phenomenon known as cosmological redshift. It is important to picture this carefully. Cosmic expansion is not best understood as galaxies flying outward through pre-existing space from a central explosion. There is no ordinary center of the expansion, as though the universe were debris spreading through a larger empty room. Instead, on the larger scales, the distances between widely separated regions of space increase over time. Galaxies are not usually racing through space like shrapnel. Rather, the fabric of space between galaxy clusters is expanding. A gentle analogy is the surface of a rising loaf of raisin bread. As the dough expands, the raisins move farther apart, not because each raisin is crawling through the dough with tiny raisin ambitions, but because the dough between them is stretching. Like all analogies, This one has limits. The universe is not a loaf, space is not dough, and galaxies are not dried fruit, despite the occasional behaviour of astronomy diagrams. But the image helps show why distant galaxies can separate as space itself changes. Modern cosmology uses a spacetime description called the Friedmann-Lamette-Robertson-Walker model. This model treats the universe as broadly uniform and similar in all directions on the largest scales. That does not mean the universe is smooth everywhere. Close up, it is full of stars, galaxies, clusters, voids, nebulae, and cosmic structure. But when averaged over enormous distances, the universe appears sufficiently uniform for this large-scale model to work extremely well. One of the strongest pieces of evidence for the early hot dense universe is the cosmic microwave background. This is ancient radiation left over from a time when the universe became transparent, roughly 380,000 years after the Big Bang. It now fills the universe as a faint microwave glow. Measurements of this radiation have been made with great precision by missions connected with the National Aeronautics and Space Administration and the European Space Agency, including the Planck mission, which mapped tiny temperature variations in the cosmic microwave background. Those tiny variations are not random decoration. They are clues to the early universe, the distribution of matter, the geometry of space, and the rate of cosmic expansion. They help scientists estimate the age, composition, and large-scale behaviour of the universe. Through them, cosmology becomes a careful measurement of changing space-time, not just a story about galaxies moving apart. This connects directly with the unity of space and time. In an expanding universe, space is not a static container, and time is not a separate clock ticking beside it. The history of the universe is the history of space-time changing. Distances between large-scale regions grow. Light stretches as space-time expands during its journey. The age of the universe and its size are tied together through the same physical description. So the title reaches cosmic scale. Space and time are joined not only when a clock moves quickly, or when gravity slows time near Earth, or when a black hole bends light. They are joined in the very evolution of the universe. The cosmos is not simply expanding into space as time passes. The expansion is a change in space-time itself, and every distant galaxy carries part of that quiet message in its light. One of the strangest consequences of relativity is that it makes the present less simple than it feels. In ordinary life, the present seems obvious. It is now. It is the moment being lived through. The past is what has already happened, and the future is what has not happened yet. This way of thinking is so natural that it feels almost beyond question. A clock ticks, a day passes, yesterday is gone, tomorrow has not arrived. The present feels like a bright moving edge, sliding forward through time and turning possibility into memory. Relativity does not erase that experience, but it does make the physical picture more complicated. In Einstein's special relativity, observers moving differently can disagree about whether distant events happen at the same time. This is the relativity of simultaneity. If two events are far apart, and no signal travelling at or below the speed of light can connect them immediately, then different observers may slice space-time into space and time in different ways. One observer may say the events are simultaneous. Another, moving differently, may say one happened before the other. This challenges the idea of a single universal present. In Newton's universe, there was one cosmic now stretching across all space. Every event in the universe could, in principle, be placed on the same universal clock. The whole cosmos shared one great present moment, whether anyone knew how to measure it or not. Relativity removes that simple background. There is no single universal slice of now that every observer must agree upon. This is where the block universe enters the discussion. The block universe is one interpretation of relativity in which past, present and future events are all understood as parts of a four-dimensional space-time structure. In this view, Events do not pop into existence only when the present reaches them. Instead, the whole pattern of events is treated as part of space-time. The universe is pictured less like a film being created frame by frame, and more like the entire film reel existing as one structure, even though a viewer experiences it scene by scene. That analogy is useful, but it must be handled carefully. The block universe is not a directly proven statement about consciousness, free will, destiny, or the felt flow of time. It is an interpretation of what relativity may imply when space-time is taken seriously as a four-dimensional structure. Physics can describe relationships between events, the paths of light, the order of causes and effects, and the measurements made by different observers. It does not automatically explain why the present feels alive, why memory points backward, or why experience seems to move. Hermann Minkowski's space-time view is central here. In 1908, Minkowski argued that space by itself and time by itself should fade into the background, leaving a united space-time as the deeper physical reality. If that picture is followed strongly, then events throughout space-time can be treated as part of one connected geometry. A birth, a star's explosion, a clock tick, a planet's orbit, and the arrival of ancient light at a telescope can all be placed within the same four-dimensional structure. But philosophers of physics and physicists still debate what this means. Some take the block universe seriously as the most natural reading of relativity. Others are more cautious, especially when trying to connect the physics of space-time with the human experience of time passing. There are also debates about whether quantum mechanics, thermodynamics, or future theories of quantum gravity may change how deeply the block universe should be understood. The physics is precise in its measurements. The interpretation is where the quiet mystery remains. It is important to separate physical ordering from psychological experience. In space-time, events can be ordered by their causal relationships. Some events can influence others, some cannot. Light cones define which events lie in the possible past or future of another event. This gives space-time a firm structure, even without one universal present. If a signal is sent and later received, all observers agree that the sending comes before the receiving. Cause and effect are protected. The psychological experience of time is different. Human beings remember the past, not the future. The brain forms memories, anticipates possibilities, and experiences change as a flowing present. This is tied to biology, thermodynamics, entropy, and the way information is stored in physical systems. Relativity does not make that experience fake. It simply shows that the universe's physical structure is not built around one universal, now shared by every observer everywhere. Light cones help keep the picture from dissolving into confusion. Even if there is no single cosmic present, causality still has boundaries. Events inside a past light cone can influence the present event. Events inside a future light cone may be influenced by it. Events outside those regions are space-like separated, meaning no signal moving at or below the speed of light can connect them directly. Observers may disagree about the order of those distant, unconnected events, but not about the order of events where influence is physically possible. So the block universe is not a license for wild claims. It does not prove that the future is consciously waiting somewhere, or that choices are illusions, or that time is just a trick of the mind. Those are much larger questions, and physics alone does not settle them so simply. What relativity does show is already strange enough. The present, as a universal physical slice through the entire cosmos, does not appear in the theory. Space and time being the same thing means more than joining rulers and clocks. It means events belong to a shared space-time structure, where different observers may divide reality into space and time differently. The present remains vivid in experience, but physics treats it with surprising caution. Beneath the feeling of now lies a quieter geometry, one in which past, present, and future are not as cleanly separated as ordinary life suggests. Spacetime is one of the most powerful ideas in modern physics, but it may not be the final layer of reality. General relativity treats spacetime as smooth and continuous. In Einstein's theory, spacetime can curve around mass, stretch through cosmic expansion, ripple as gravitational waves, and shape the paths of planets, stars, light, and clocks. It behaves like a geometry, and that geometry can be described with extraordinary precision. On large scales, this picture works beautifully. It explains the orbit of Mercury, the bending of starlight, gravitational time dilation, black holes, gravitational waves, and the expanding universe. As scientific resumes go, that is a fairly strong one. But the universe also contains another great theory, and it speaks a very different language. Quantum mechanics describes matter and energy in terms of probabilities, quanta, particles, waves, fields, and measurement. It does not begin with smooth geometry. It begins with the strange behavior of atoms, electrons, photons, and the microscopic world. It explains why atoms are stable, why stars shine, why chemistry works, why semiconductors can exist, and why the modern technological world is not just a collection of very confident wires. The problem is that general relativity and quantum mechanics are both extraordinarily successful, yet they do not fit together cleanly. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes the other known forces and particles using quantum fields and probability. When gravity is weak, or when quantum effects can be treated separately from space-time curvature, physicists can work successfully. But in the most extreme places, the disagreement becomes unavoidable. Black hole interiors are one example. Classical general relativity predicts a singularity, where curvature becomes infinite and the theory reaches a breakdown point. The earliest moments of the universe are another example. If the universe began in an extremely hot, dense state, then both quantum effects and intense space-time curvature would have mattered together. In those regimes, physicists need a theory that can describe gravity and quantum physics at the same time. That deeper theory is usually called quantum gravity. Quantum theory itself grew from many discoveries. Max Planck introduced the idea of energy quanta in 1900 while studying blackbody radiation. Niels Bohr used quantum ideas to build an early model of the atom. Werner Heisenberg developed matrix mechanics and the uncertainty principle. Erwin Schrödinger developed wave mechanics and the wave function. Paul Dirac connected quantum mechanics with special relativity and predicted antimatter. These figures did not set out merely to make physics harder to explain before bedtime, though it can sometimes feel that way. They were responding to experiments that classical physics could not explain. Quantum mechanics complicates space-time because it raises the question of whether space-time itself should also have quantum properties. If matter and energy are quantum and matter and energy shape space-time, then can space-time remain perfectly smooth at every scale? Or does it become uncertain, grainy, fluctuating, or emergent at extremely tiny distances? Physicists do not yet know the final answer. One place where this uncertainty is often discussed is the Planck scale. The Planck length is an unimaginably tiny scale, roughly 35 powers of 10 smaller than a metre. That is not merely small like a speck of dust, or small like an atom, or even small like an atomic nucleus. It is vastly smaller than the scales directly explored by current particle accelerators. At around this scale, many physicists expect that the smooth space-time of general relativity may no longer be enough. A deeper framework may be needed, one that can handle quantum effects and gravitational geometry together. Several approaches have been proposed. String theory suggests that the most basic ingredients of nature may not be point-like particles, but tiny one-dimensional strings whose vibrations correspond to different particles. Edward Witten has been one of the major figures in developing this field. String theory naturally includes gravity in its framework, but it has not yet been confirmed experimentally as the final theory of nature. Loop quantum gravity takes a different route. It attempts to quantize space-time geometry itself, suggesting that space may have a kind of discrete structure at the deepest scale. Abhay Ashtekar is one of the key figures associated with this approach. Like string theory, loop quantum gravity remains an active research program rather than a proven description of reality. There are also ideas in which space-time may be emergent. In these views, space-time might not be fundamental at all. It could arise from something deeper, such as quantum information, entanglement, or relationships between more basic ingredients. Entanglement is a quantum connection between systems that cannot be fully described independently, even when separated. Some modern research suggests that the geometry of space-time and the pattern of quantum entanglement may be linked in profound ways, but this is still a frontier, not a settled conclusion. This is where scientific honesty matters. It would be tempting to say that physicists have already discovered what space-time is made of, or that one theory has clearly solved everything. But that would go too far. General relativity and quantum mechanics remain two great pillars of modern physics, and the bridge between them is still incomplete. The mystery is real because the evidence points to a missing deeper picture, not because anyone needs to sprinkle extra mystery on top like scientific paprika. So space and time being unified was a profound step. Minkowski spacetime showed that distance and duration belong to one structure. General relativity showed that this structure curves, evolves, and responds to mass and energy. But unity does not necessarily mean finality. Space-time may be the deep architecture of the universe at the scales we can describe, while still emerging from something deeper at scales far beyond ordinary reach. The title remains true within relativity. Space and time are inseparable parts of one physical geometry. But the larger question remains open. That geometry may not be the bottom floor of reality. It may be a beautifully smooth surface laid over a deeper quantum foundation, one that physics is still slowly, carefully, and very patiently trying to understand. Relativity can sound as if it belongs only to the far edges of reality. Black holes, merging neutron stars, distant galaxies, near light-speed particles, expanding space-time, and clocks behaving strangely near massive objects all seem comfortably removed from everyday life. It is easy to imagine relativity as something that happens somewhere else, far beyond the kettle, the sofa, and the mildly accusing pile of laundry. But space-time physics is not remote from ordinary reality. It is built into some of the most precise technologies humans use. The effects are usually tiny, because everyday speeds are slow compared with light, and Earth's gravity is weak compared with a black hole. Tiny, however, does not mean unimportant. Modern technology often lives in the world of tiny differences, where billionths of a second can matter, and a small timing error can become a large navigation error. The clearest practical example is the Global Positioning System. Satellite navigation works by timing signals sent from satellites orbiting Earth. A receiver, such as a phone or navigation device, compares the arrival times of signals from several satellites. Because light and radio signals travel at a known speed, those timing differences allow the receiver to calculate its position. The basic idea sounds simple. Measure time carefully enough, and time becomes a map. But the clocks on Global Positioning System satellites do not tick at exactly the same rate as clocks on Earth's surface. Special relativity matters because the satellites are moving rapidly relative to the ground. Their motion causes their clocks to tick slightly more slowly from the perspective of clocks on Earth. General relativity also matters because the satellites orbit far above Earth's surface, where Earth's gravity is weaker. Higher in the gravitational field, their clocks tick slightly faster than clocks on the ground. These two effects partly oppose each other, but the gravitational effect is larger for the satellites. The result is that satellite clocks would drift from Earth-based clocks if relativistic corrections were ignored. The difference may sound small, but satellite navigation depends on extremely precise timing. Without corrections from special relativity and general relativity, position errors would grow quickly and the system would become far less accurate. In other words, finding the nearest petrol station, airport, hiking trail, or suspiciously well-reviewed sandwich shop quietly depends on the fact that space-time is real. Atomic clocks make this possible. Atomic clocks use the regular behavior of atoms to define time with extraordinary precision. Cesium atomic clocks have long been central to official timekeeping, while newer optical atomic clocks can reach even higher levels of precision. These instruments do not measure time by a swinging pendulum or a turning gear, but by the stable frequencies associated with transitions in atoms or ions. They are among the most precise measurement tools ever built. National metrology laboratories maintain and compare these standards. The National Institute of Standards and Technology in the United States, often abbreviated as NIST, is one important organization involved in precision measurement and timekeeping. Similar institutions around the world contribute to international time standards. Their work may sound quiet, but it supports communication networks, scientific experiments, navigation systems, financial systems, and many technologies that depend on synchronized timing. Civilization, it turns out, runs partly on clocks being extremely well behaved. Relativity also appears in particle accelerators. At CERN, the European Organisation for Nuclear Research, particles are accelerated to speeds very close to the speed of light. At those speeds, Newtonian physics is no longer enough. Relativistic effects determine how particles gain energy, how their motion is described, and how experiments are designed. Protons in the Large Hadron Collider move so close to light speed that their behavior must be treated using special relativity and quantum field theory. Without relativity, the machine would not make physical sense. This is not only true for the largest accelerators. Smaller particle accelerators are used in medicine, industry, and research. Particle beams can be used in cancer treatment, including proton therapy, where charged particles are directed into tumours with carefully controlled energies. The full medical practice depends on many areas of physics, biology, engineering, and imaging, so it would be misleading to say relativity alone makes it possible. But when particles move at high speeds, relativistic physics becomes part of the accurate description of their energy and motion. Synchrotron radiation facilities also rely on high-speed charged particles. When electrons are accelerated around curved paths at speeds close to the speed of light, they emit intense light known as synchrotron radiation. This light can be used to study materials, proteins, chemical structures, fossils, batteries, and many other systems in remarkable detail. Facilities around the world use these beams as powerful scientific tools. Again, relativity is not a decorative extra. It belongs to the physics of fast-moving particles and the radiation they produce. High-precision electronics, communication systems, astronomical observatories, and laboratory measurements all touch this deeper world in different ways. Not every device in daily life needs a full calculation from general relativity, and it would be excessive to blame spacetime every time a printer refuses to cooperate. But modern measurement has become precise enough that relativistic effects can no longer be treated as distant curiosities. They appear wherever timing, motion, gravity, and high speeds must be understood accurately. Astronomy depends on relativity as well. Observations of gravitational lensing use the bending of light to map mass in galaxies and galaxy clusters. Pulsars, which are rapidly rotating neutron stars, can act as precise cosmic clocks and test gravity in extreme conditions. Gravitational wave observatories detect tiny stretches and squeezes in space-time from distant mergers. These are not everyday household technologies, unless someone has a very unusual living room, but they show that modern science now measures space-time directly and repeatedly. The quiet lesson is that space-time has become part of the infrastructure of modern life. It guides satellites, it corrects clocks, it shapes particle accelerator physics, it helps astronomers interpret light from distant objects, it supports the measurement systems behind navigation, communication, and scientific discovery. The idea that once sounded like a strange philosophical merger of space and time now sits behind practical systems people use without thinking. This brings the whole subject back down to Earth. Space and time being joined is not only an idea for black holes and cosmic expansion, it matters because the universe follows the same principles everywhere. The same relativity that explains time near a massive star also helps keep satellite navigation accurate. The same space-time that ripples during black hole mergers also gives meaning to precision timekeeping in laboratories. The ordinary world still feels ordinary, because human senses are not built to notice tiny relativistic corrections. A phone screen does not look like a portal into curved space-time. A satellite navigation route does not announce that Einstein has politely assisted with the journey. Yet beneath the surface, the strange geometry is there. Modern technology has become precise enough to reveal that space and time are not just abstract ideas. They are working parts of the world, quietly shaping the measurements that help modern life move. So what does it really mean to say that space and time are the same thing? It does not mean that space and time feel the same. They do not. Space is experienced as distance, direction, area, volume, and location. Time is experienced as duration, change, memory, aging, and sequence. A room and an hour are not interchangeable. A meter is not a second. A clock is not a ruler, unless someone has built a deeply unhelpful piece of furniture. The meaning is more precise and more interesting. In modern physics, space and time are inseparable aspects of one physical structure called space-time. They are not identical in everyday experience, but they are joined in the deeper geometry described by relativity. What one observer measures as distance, and what another observer measures as duration can depend on motion. Gravity can change the shape of space and the rate of time together. Light, causality, planets, black holes, and the expanding universe all reveal that space and time are not independent backgrounds. They are parts of one connected framework. That idea did not appear all at once. It was reached slowly, by following problems that refused to stay politely inside older theories. Isaac Newton's universe gave science a magnificent foundation. In Newton's view, space was absolute, a fixed three-dimensional arena in which objects moved. Time was absolute too, a universal clock flowing evenly throughout the cosmos. This picture worked extraordinarily well. It explained falling objects, projectiles, planetary orbits, tides, and the motions of everyday matter. It remains one of the greatest achievements in the history of science. But then light began to disturb the picture. James Clerk Maxwell unified electricity and magnetism into electromagnetism, and his equations showed that light was an electromagnetic wave travelling at a fixed speed in vacuum. That discovery was beautiful, but it came with a puzzle. If light was a wave, many physicists expected it to move through a medium called the luminiferous ether. The Michelson and Morley experiment in 1887 searched for Earth's motion through that ether and did not find the expected result. The missing ether wind became one of the clues that the old picture of space and time had a serious problem. Albert Einstein's special relativity, published in 1905, changed the rules. It began with two central ideas. The laws of physics are the same for all observers moving steadily, and the speed of light in vacuum is the same for all such observers. If the speed of light is fixed, then distance and duration cannot both remain absolute for everyone. Moving clocks are measured to tick more slowly. Moving objects are measured as shorter along their direction of motion. Events that seem simultaneous to one observer may not seem simultaneous to another observer moving differently. These effects are strange, but they are not random. Hermann Minkowski showed in 1908 that they make sense when space and time are treated as one four-dimensional structure. Minkowski's space-time turned special relativity from a collection of surprising effects into a deeper geometry. Events became points in space-time, each with both a where and a when. Observers could disagree about space and time separately, while still agreeing about deeper spacetime relationships. That is the central lesson. Time is not secretly just space. Space is not secretly just time. The deeper point is that nature preserves a four-dimensional structure beneath the separate measurements of distance and duration. Observers may divide that structure differently depending on their motion, but they are not inventing separate realities. They are describing the same space-time from different frames of reference. Then general relativity made the idea even more powerful. Einstein's theory, completed in 1915, showed that gravity is not best understood as a simple force pulling objects through fixed space. Instead, mass and energy curve space-time. Objects in free fall follow geodesics, the natural paths through that curved geometry. Planets orbit because space-time around the sun is curved. Light bends near massive objects because light also follows space-time geometry. Clocks tick at different rates in different gravitational conditions because time is part of that same geometry. This is where the title becomes deepest. Gravity does not only bend paths through space, it also changes the flow of time. A clock near sea level ticks extremely slightly more slowly than a clock at higher altitude. A satellite clock must be corrected for both motion and gravity. The global positioning system works partly because engineers account for relativity. The same theory that describes black holes also helps modern navigation avoid becoming impressively lost. Black holes reveal the extreme version of this unity. A black hole is not merely an object sitting inside ordinary space and time. It is a region where space-time curvature becomes so severe that an event horizon forms. Beyond that boundary, light cannot escape to distant observers because all future paths lead inward. Time near a black hole differs dramatically depending on the observer. Space and time stop behaving like calm, separate backgrounds and become the central physical reality. Gravitational waves confirm that space-time is not passive. When black holes or neutron stars spiral together and merge, they send ripples through space-time itself. The laser interferometer, Gravitational Wave Observatory, detected such waves directly in 2015. The measured effect was incredibly tiny by the time it reached Earth, but it carried information from a violent event more than 1 billion light-years away. Space-time can stretch, squeeze, ripple, and carry energy. The stage itself can move. On the larger scales, cosmology shows that space-time has a history. Alexander Friedmann and Georges Lemaitre found expanding universe solutions within general relativity. Edwin Hubble's observations helped show that distant galaxies generally appear to be receding. The expansion of the universe is not best pictured as galaxies flying through pre-existing space from a central explosion. It is better understood as large-scale distances growing, because space-time itself is changing. The cosmic microwave background, measured in detail by missions including Planck, carries ancient evidence from the early universe and helps reveal the shape, age, and composition of the cosmos. So space-time unifies many ideas that once seemed separate. It connects distance and duration. It connects motion and measurement. It connects gravity and geometry. It connects light cones and causality. It connects black holes, gravitational waves, satellite clocks, and cosmic expansion. It is one of the most important frameworks in modern physics, because it does not merely describe where things are and when things happen. It describes how where and when belong together. And yet the ordinary world remains meaningful. A table is still in a room. A train still arrives at a station. A day still passes from morning into night. Newtonian intuition works extremely well because human life unfolds at low speeds compared with light and in weak gravitational fields compared with black holes. Relativity does not make common sense useless. It explains why common sense works in ordinary conditions and why it must be expanded when nature is measured more precisely. That may be the most calming part of the idea. The universe is stranger than it feels, but not unstable. Space-time is not a reason to distrust reality. It is the hidden structure that helps reality remain coherent. It lets different observers measure space and time differently, without breaking cause and effect. It lets light define the boundaries of influence. It lets planets orbit, clocks compare, galaxies recede, and gravitational waves carry messages across cosmic distance. Space and time are the same thing, only in the sense that they are woven into one physical geometry. They remain different in experience, but inseparable in the deeper language of relativity. No one has ever moved through space without also moving through time. No one has ever measured time except from somewhere in space. Every event has both a location and a moment, and every life unfolds along a path through space-time, carried gently through the joined fabric of distance, duration, motion, and memory. So, why are space and time the same thing? The calmest answer is that modern relativity describes them as inseparable parts of one, four-dimensional structure called space-time. Space and time are not the same in ordinary experience. A distance is not a duration. A clock is not a ruler. A room is not an hour, unless the hour is being spent in a waiting room, in which case the confusion becomes emotionally understandable. But in the deeper physical description revealed by relativity, space and time do not stand apart as two independent backgrounds. They belong to one structure, and the universe measures itself through both together. Classical physics treated them differently. In Isaac Newton's universe, space was the fixed arena where objects moved, and time was the universal clock that ticked evenly everywhere. That picture was extraordinarily successful. It still works with beautiful accuracy for everyday motion, weak gravity, engineering, navigation, falling objects, projectiles, tides, and the broad motions of planets. It is not foolish or obsolete in the ordinary world. It is a powerful approximation, one that remains woven into practical science. But light began to disturb that simple separation. James Clerk Maxwell's theory of electromagnetism showed that light was an electromagnetic wave, travelling at a particular speed in vacuum. The Michelson-Morley experiment failed to find the expected motion through the luminiferous ether. The old picture of fixed space and universal time began to strain. Light seemed less like an ordinary object moving through a background, and more like a fixed feature of physical law. Albert Einstein's special relativity transformed that problem into a new understanding. If the laws of physics are the same for observers moving steadily, and if the speed of light in vacuum is the same for all such observers, then measurements of distance and duration cannot remain absolute for everyone. Moving clocks are measured to tick more slowly. Moving objects are measured as shorter along their direction of motion. Two distant events that seem simultaneous to one observer may not seem simultaneous to another observer moving differently. Hermann Minkowski then gave this strange new physics its deeper shape. In 1908, he showed that Einstein's relativity could be understood as space-time, a union of 3 dimensions of space and 1 dimension of time. Events are not merely things that happen somewhere while time passes separately above them. Every event has both a where and a when. A flash of light, a falling stone, a pulse from a distant star, a clock tick, and a quiet breath before sleep all belong to a connected map of space-time. General relativity made that map active. Einstein's theory of gravity showed that mass and energy curve space-time itself. Gravity is not merely a force pulling objects through a fixed background. It is the geometry of space-time guiding matter and light along natural paths. The sun curves space-time, and Earth follows that curvature in its orbit. Massive objects bend the paths of light. Clocks closer to mass tick more slowly than clocks farther away. Gravity changes space and time together. This is why gravitational time dilation matters so much. Time does not flow at exactly the same rate everywhere. A clock at sea level ticks extremely slightly more slowly than a clock at higher altitude. Satellite clocks used by the Global Positioning System must account for both special relativity and general relativity. Relativity is not only a cosmic idea reserved for distant galaxies and black holes, it is part of the careful timing that helps modern navigation work at all. Black holes reveal space-time at its most extreme. A black hole is not simply an object sitting inside ordinary space and ordinary time. It is a region where space-time curvature becomes so severe that an event horizon forms beyond which light cannot escape to distant observers. Near a black hole, time and space behave in ways that show their unity more powerfully than almost anywhere else. The future paths available to light and matter are shaped by geometry itself. Gravitational waves add another piece of the same story. When black holes or neutron stars spiral together and merge, they send ripples through space-time. The laser interferometer. Gravitational wave. Observatory directly detected such waves in 2015, measuring an incredibly tiny stretching and squeezing caused by a collision more than 1 billion light-years away. Space-time is not a passive stage. It can move, ripple, carry energy, and bring news from some of the most violent events in the universe. Even the expanding universe belongs to this same idea. Cosmology applies general relativity to the universe as a whole. The expansion of the universe is not best pictured as galaxies flying through pre-existing empty space from one central point. It is better understood as the growth of large-scale distances as space-time itself changes. The cosmic microwave background, distant galaxies, and the large-scale structure of the cosmos all help reveal the history of space-time. Yet none of this erases ordinary life. Space and time still feel separate because human beings live at low speeds compared with light and in weak gravitational fields compared with black holes. A cup still sits on a table. A day still passes. A train still moves from one station to another. Newtonian intuition remains useful because it describes the calm middle ground where human experience unfolds. Space-time is not a decorative mystery. It is a precise scientific framework supported by experiments, astronomical observations, atomic clocks, satellite navigation, particle accelerators, gravitational lensing, and gravitational wave detections. It is strange, but it is not vague. It is one of the most reliable ways physics has found to describe reality. And still, deeper questions remain. General relativity treats space-time as smooth and continuous, while quantum mechanics describes the microscopic world through probabilities, quanta, and fields. Physicists do not yet know whether space-time is fundamental or whether it emerges from something deeper, perhaps connected with quantum information, entanglement, or a future theory of quantum gravity. The unity of space and time was a profound discovery, but it may not be the final layer. For now, the quiet lesson is enough. Every moment is also a location. Every location is known through time. No one moves through space without also moving through time, and no one experiences time except from somewhere in space. Reality is woven from both more intimately than ordinary intuition can easily picture, and beneath the familiar world of rooms, clocks, stars, and passing days, space-time holds the universe together in one calm, hidden geometry.